Hello everyone, Engineering Statistics and Linear Algebra. Today we do discuss a Gaussian Bi-variate Random variables. Let us know the meaning of a Gaussian random variable. It is a concept of model number 1. It is already discussed. Today we do highlight it once again. Normal distribution, it is also called as a Gaussian distribution. It is the important probability distribution in statistics because it fits many natural phenomena. For example, heights, blood pressure, measurement error, and IQ scores follow the normal distributions. A normal distribution, it is a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than the data far from the mean. In the graph, a normal distribution will appear as a bell curve. In these three examples, we can observe the peak point that is called as a mean, and curve is symmetric about this mean. A Gaussian distribution, it is a bell-shaped curve, and it is assumed that during any measurement values will follow the normal distribution with an equal number of measurements above and below the mean value. With this background, let us discuss a PDF of the normalized Gaussian random variable. It is a concept of a single random variable. Fz of z, it is called as a PDF of a single random variable, especially a Gaussian random variable. And it is defined with this equation where this z is a capital Z considered as a random variable. This is a small z considered as an independent variable, where independent variable z is any random variable varying from minus infinity to plus infinity. The associated cumulative distribution function is given by this equation. So we know the relations between PDF and CDF. Uh, CDF is an integration of PDF, or else a PDF is a differentiation of a CDF. We know these two. And the properties of normalized Gaussian random variables are a PDF is non-negative and area under the curve is always 1. A CDF is continuous and non-decreasing from 0 on the left to the 1 on the right. The derivative of the CDF existed anywhere. So with this background, let us we discuss a Gaussian bivariate probability density function. Consider two random variables z1 and z2, they are capital, and consider two independent variables z1 and z2, they are small. And for this condition, let us we define a Gaussian bivariate probability density functions. This first term, this term indicates a Gaussian bivariate probability density functions, and it is defined here. This rho z, it is called as a correlation efficient. z1 and z2 are the independent variables, and this is holds good under these two conditions. So this correlation coefficient having the values from +1 to -1, but for this Gaussian bivariate probability density function, it must be less than 1. So if it is more than 1 means this term becomes imaginary term, so that to avoid that problem, rho z should be less than 1. Similarly, and a square root of this term should be greater than 0, then only it cannot have any imaginary term. So this formula should be remembered by you people. So example for that Gaussian bivariate PDF is here, and they are bell-shaped curve. Instead of z1 and z2, and x and y independent variables are used here. So there we have used z1 and z2. Here the two different x and y independent variables are used here. All right. For that given bivariate PDF, next let us calculate probability densities. They are called as single random variable probability density functions. We know to calculate a probability density function of Z1, a bivariate PDF should be integrated with respect to Z2. Already this concept was discussed, and this is the given bivariate PDF. Let us consider this term, and it should be written in another form using a completing square technique. Consider this term and consider this row Z, 2 into row Z half is row Z square, and adding row Z square into Z1 and subtracting it to this equation. We'll get, let us modify this equation, write this Z2 square at the first, adding and subtracting these two terms, and using a minus b whole square formula here. First, these three terms, they are in this form, so that it can be adjusted to a minus b whole square format, so that the given equation can also be written in this form. So from these two terms, z1 square is a common, so that 1 minus rho z square can be written inside the bracket. Alright, so this is a given bivariate PDF. In this bivariate PDF, it is considered and it is written in different format. Now, consider this complete term. Consider this complete term and divide this 2 into 1 minus root z whole square to first term and to the second term. That is done here. It is divided to both the terms. Later, it is under exponential, so e to the power a plus b can be written as e to the power a into e to the power b. You can consider here this term and this term can be cancelled. As a result, exponential of minus z1 square by 2 into exponential of this term can be written. The given bivariate PDF can also be written in this format. Okay, so everything is written as it is here. So this is the modification should be done to the given bivariate PDF while calculating f z1 of z1. We know this formula. Next, the given PDF is modified and apply this bivariate PDF inside the integration, and this should be integrated with respect to z2. In this integration, z1 terms are constants, so take them outside. So this term 2 pi and rho, they all are constant, so that take them outside. Only remaining terms are z2 terms. And using a concept of a substitution method, using change of variable, substitute u is equals to this complete term. So z2 minus rho z into z1 divided by square root of 1 minus rho z square. That should be replaced by a term u. Now differentiate this equation. Differentiation of u is du, and this is constant. Differentiation of z2 is dz2, and it is a constant, it is 0, so that this dz2 can be written as this term. Alright, after a change of variable concept, these terms will be written as it is. dz2 can be written using this formula, and exponential of it becomes minus u square by 2. So take it outside. This term and this term can be cancelled. Only remaining terms are e to the power minus z1 square by 2 and 2 pi, and it is nothing but a gamma function. It can be replaced by square root of 2 pi. As a result, the remaining term is exponential of minus z1 square by 2 divided by square root of 2 pi. So a probability density function of z1 is calculated from a given bivariate probability density functions. Alright, so f z1 of z1 is calculated here. Similarly, f z2 to f z2 of z2 can also be calculated by following the same procedure. As a result, we will get same thing. Instead of z1, it is z2. So these two calculations are very important as an examination point of view. So keep these derivations as ready as possible. Alright, let us discuss the properties of a Gaussian bivariate probability density function. So a probability density function should be greater than or equals to 0 for any value of z1 and z2, and area under the curve should be equals to 1. Volume, the area under the volume is always 1, so you can consider here. And mean and variance of random variables z1 and z2 are always 0. Expectation of z1 is 0, expectation of z2 is 0. In general, it is called as a mean of a random variable z is always 0 here, because it is having equal and opposite area, so that as a result a mean of random variables are 0 here. And always variance of z1 and z2 are in general z is always 1 here. It is a property number 3. Then property number 4, correlation. The correlation coefficient and covariance are all equal. It is called as a covariance. Sorry, it is called as a correlation. It is called as a covariance, and it is called as a correlation coefficient. They are one another same. Then fifth property, let us consider bivariate random variables x1 and x2. They are defined in terms of z1 and z2. You can observe here x1 and x2 are different random variables. They are defined in terms of z1 and z2. It is a concept called bivariate transformation. We know the definition of covariance. Covariance of x1 and x2 can be written using this formula. Substitute the value of x1 here. X1 is nothing but this one minus of this. Substitute the value of x2 here. Alright, so these two terms are cancelled. These two terms are cancelled, and remaining terms are these two. And a row of x1 and row of x2 are constant. Take them outside. The remaining terms are correlation of z1 and z2. We know that correlation of z1 and z2 is equals to covariance of z1 and z2. That is also equals to correlation coefficient. So this term is replaced by covariance coefficient, correlation coefficient. All right, so that this correlation of x1 and x2 can also be written as rho of x1 and x2 divided into standard deviation of x1 and standard deviation of x2. This is the definition of a correlation coefficient. Correlation coefficient, it is the ratio of covariance of x1 and x2 divided by standard deviations of x1 and x2, so that it can be replaced by multiplication of correlation coefficient and standard deviations, and these two terms can be cancelled, and correlation coefficient of these two random variable, it is equals to correlation coefficient of a z. This is the property of a Gaussian bivariate random variable here. All right, so for a Gaussian bivariate random variable, correlation, covariance and correlation coefficient are one another same. Keep that point in your mind, it is needed for the further calculation. If bivariate Gaussian random variables are uncorrelated, what is the meaning of this uncorrelated? Covariance is zero. Covariance is zero, then we can say that those two random variables are uncorrelated. If covariance of z1 and z2 is zero, means a correlation coefficient is also zero, correlation is also zero. Let us make use of this property for the further calculation. So it is called as a bivariate PDF. It is equals to multiplication of individual PDF. If this is the case, then we can say that those two random variables are independent in nature. As a conclusion, if the covariance of z1 and z2 is 0, then we can say that they are uncorrelated. If they are uncorrelated, then definitely they are independent. So this is the property of a Gaussian bivariate random variable here. So let us prove this one. So this is a bivariate PDF. In this bivariate PDF, the covariance of z1 and z2 is 0. If it is 0, means this term is also 0. Then replace a correlation coefficient 0 in this equation. So it becomes 1, it becomes 0, it becomes 1. After simplification, only 1 by 2 pi is remaining, exponential of only z1 square plus z2 square divided by 1 by 2. Alright, is it equals to multiplication of z1 of f z1 of z1 and f z2 of z2? Let us see. We have already calculated marginal densities. They are already calculated here. If these two are multiplied, then can we get this equation? Obviously. So 1 by square root of 2 pi, 1 by square root of 2 pi, it is what, 1 by 2 pi. So these two are multiplied, as a result exponential of addition can be written here. So if z1 and z2 are uncorrelated, then definitely they are independent. It is a property of a Gaussian random bivariate random variable. So this is what the explanation of a Gaussian bivariate random variable. So not only z1 and z2, for any random variables, they are independent. We can consider any number of random variables. If they are uncorrelated each other, all these random variables, or if they are uncorrelated with each other, then definitely they are independent each other. So with this, today we do wind up this discussion. In next class, we do discuss the sum of two independent random variables. If you have any doubts, means feel free to ask me, and like, share, comment on the video, and don't forget to subscribe the channel. Thank you.